Alright, we're going to look at volcanism. We're going to be looking at eruptions and different igneous processes that are associated with volcanism. And here we've got a map of the Pacific Ocean, and these are just different plate boundary maps, and we'll see that this is called the Ring of Fire. And this is going to be something that will be consistently coming back just because there's so much variety of volcanism here. And roughly 80% of all volcanism that takes place on the Earth takes place in and around this area. So a very active region geographically. And you'll see that different volcanoes have different characteristics, that they do not erupt the same, and they have quite the different storylines to them. So one could say that they actually have personality. So here we have an attempt at some humor, and here's a video that is embedded on the slide that has a nice little kind of a 3 or 4 minute backdrop onto the morphology or the structure of what is inside a volcano. So here we go. This is a picture of Mount St. Helens. Now Mount St. Helens is located in the Cascade Range in the Pacific Northwest. It is in Washington. And this is what it looks like before, right? We see this very nice, just nice symmetrical mountain, a volcano here. And the next slide we'll see, well, it doesn't look like that anymore. So the igneous world of volcanism is based on a simple concept. How viscous is the magma? So the more silica, the more viscous, and the more difficult it is for gases to escape. So high silica, or felsic magmas, erupt with tremendous energy and in a short duration of time. And you'll see that here, Mount St. Helens, after this whole side of the volcano actually eventually collapsed, and then it decreased the total pressure above the magma chamber, and that led to the eruption. So basaltic magmas contain around 50% silica, where felsic magmas contain closer to 70% silica. So if you find granite or a rhyolitic magma, then you find the ingredients for a violent eruption. So we have the before and after of Mount St. Helens, and we'll get into the storyline of it in the near future. But sometimes Mount St. Helens becomes the poster child of volcanism. So here we go, and we've looked at this many times, just about how mafic or basaltic has a lower, the magma has a lower silica content, whereas your rhyolitic or granitic has much higher. And what we're looking at here is, we're going to be calling this, and we have a couple times before, but just make sure we go back to this, the viscosity of magma and the quantity of dissolved gases and the ease at which the gas can escape determines the nature of the volcanic eruption. So we have basalt lead to mild eruptions, right? Gases escape very easily. In granitic or rhyolitic, these are violent eruptions. The sticky magma slows down the outflow of gases. And now a concept that we'll add to the mix is the volatiles. Volatiles in magma. So all magmas contain water. It's in a vapor form, but it's still there. And other volatiles, other gases, that are held in solution by the pressure of the overlying rock. As a part of the upper part of the magma, as the reservoir rises, gases are released like that of a soda container, allowing gases to escape. Well, as the pressure decreases, as the magma approaches the Earth's surface, gases are more able to escape quickly and explosively. So if I look at this cross-section of the Earth, here I have this partial melting in the uppermost asthenosphere, and we get these rising basaltic magma through the lithosphere, right? It continues to rise. It then ponds, right? I get this ponding of magma, and it differentiates, right? We can say, well, it goes through Bowen's reaction series as it cools, and then we get this silica-rich magma, and this can potentially have yet a secondary kind of a ponding or a magma chamber, kind of this reservoir here that's going to fuel the volcanism at the surface. So we have a couple different scenarios here playing out, and we can look at that with a cross-section. So if I look at Hawaii, we can take a look here at basaltic flows. We have and Pahoehoe lavas of Hawaii. That these are mild eruptions from basaltic composition magma. They lead to lava flows, and these are what built the islands of Hawaii. This over here is the flow, very cindery, and these over here are ropey. These are the Pahoehoe, and just two different types of volcanoes, even just on some of the most famous volcanoes on the planet of Hawaii. So if I look at the anatomy of a volcano, I would see that I have this this plumbing system, this conduit system that is like a series of pipes. So when I say the word conduit, we're really talking about the internal plumbing network, or the path of how liquid rock mobilizes, how it moves from the hot depths into finding its way to the surface. So as it goes from a magma to a potential lava, we're really looking at the network that's transferring it from depth to the surface. And we have a crater, and the crater is also generally associated with a vent, right? The vent is just a location where you take the inner stuff and you put it back out to the atmosphere. But the crater is the surface opening. And here's a picture of a crater of Mount Vesuvius, and we'll be studying Mount Vesuvius here in just a few moments, or in a couple slides coming up. And then lastly, pyroclastic material. This is the hot gases that are infused with ash and rock. The pyroclastics are the debris that makes it up into the atmosphere, this plume here, that eventually rains down, and very dangerous. Pyroclastic material are very hot. They are hot gas laden, and they can be really small pieces of ash and dust, and they can be really large to the size of bombs. So really a broad range of sizes of particulates within pyroclastic material. So let's go back to Hawaii for a minute. If I look here, the Hawaiian Islands are all shield volcanoes that formed from basaltic magma rising from the deep within the earth and erupting. Right, the islands of Hawaii begin at the ocean floor. We're a hot spot. Very key concept here. This is the first we're going to be talking about what a hot spot is, and I'll talk about it here in a moment just on this map. But it's pumping up basaltic rock through the Pacific crust, leaving volcanic landforms behind where they once stood, actively erupting at some point in their volcanic life. Shield volcanoes have a characteristic very gentle slope, roughly 5 degrees, from continual lava flows from the central vent. And these flows are generally not explosive due to the low viscosity basaltic magma. Mauna Loa on the Big Island is the world's largest mountain in the world. It rises more than 30,000 feet. That's over 6 miles above the ocean floor. So here's an aerial view. We've got Mauna Kea, we have Mauna Loa, we have Hualai. You say it, I'll let you do it. And Kahala. So these are just islands or volcanoes on the Big Island. So let's look at what a hotspot is. And I want you to see that here we have Emperor Seamounts. These are underwater, once volcanic active volcanoes, but now they're extinct. Here's where we see this chain of Hawaiian islands. And the Pacific plate, it's kind of interesting because this arrow here is the Pacific plate is moving plate tectonically this way, and this hotspot is this fixed location. So as the Pacific plate rests over the hotspot for any length of time, islands form just from continual basalt flows. So these islands have been radiometrically dated to have this timeline. This is between 3.8 and 5.6 million years ago. Oahu, that's Kauai. Oahu is 2.2 to 3.3 million years ago. We have Molokai between 1.3 and 1.8. We have Maui less than 1 million, and then we have the Big Island of Hawaii right now is presently over this hotspot, and it's being fueled by these mantle plumes, these deep mantles that are cranking out basaltic magma. So it's pretty cool. It's a pretty cool geologic storyline. So shield volcanoes, the Hawaiian Islands. Mauna Loa, this is a volcano that was built from the ocean floor. This height leads to the Big Island of Hawaii above sea level. So that's all a part of that whole mountain system. So continuous flows of magmas take place over hundreds of thousands to millions of years. These are what build the islands, and they're still active today. When I say they, I mean the hot spot is. There are smaller volcanoes, but the Big Island of Hawaii is definitely situated over this hot spot. And the Pacific plate, when we look at plate tectonics, is moving over a hot spot, and islands form as the plate moves over it. So here's a couple different pictures. Here's a shield volcano, Mauna Loa, and it's a really, really large one. It even has a caldera. We'll talk about that soon. And it's so much larger than Mount Rainier. Just what we think of as big volcanoes, really when we compare it to Hawaii, even though we only see this area right here, right above sea level, it actually goes all the way down to the ocean floor. So there's a lot more that we don't see or pay attention to. So cinder cone volcanoes. Cinder cones are like scoria cones, which are built from ejected lava fragments that appear as cinders or clinkers. Actually, when I say lava, they're really not. They're more like they're cinders. It's really not the type of lava that you think of. And they harden while they're in flight or while they're mobilizing through the central vent of the volcano itself. And these form very steep slopes. So if you see a steep sloped volcano, it's likely a cinder cone. And these range in size from fine ash to bombs that may exceed a meter in diameter. But they're mostly pea to walnut sized. And the magma that comes out here that becomes lava on the surface is vesicular, it's fine-grained, and it's reddish-brown in color. And cinder cones happen to be the most prevalent or abundant of all the three types of volcanoes. And scoria is compositionally similar to basalt, only that it's vesicular. So here's another picture of a common or a standard cinder cone volcano. And we have the material that has been erupted from the volcano that builds up the volcano structure itself. Moving on, let's look at this cinder cone picture here. So I have my internal plumbing system. It's very common. Here I have what's called a Holocene cinder cone volcano here. I have, I'll let you interpret that one here in Hawaii. But these erupt very little lava, if any. These are grainy cinders that erupt are basaltic, or they can even be intermediate, which we would say andesitic. And these are the steepest of the three primary volcanoes, the slopes of the cinder cones. And cinder cones can also occur on any type of volcano, including small parasitic cinder cones on a large cinder cone. So you can have a large cinder cone, and you can have a parasitic cinder cone. You can have a shield volcano, and you can have a parasitic cinder cone. It's simply whatever's left in the magma chamber that's going to fuel the eruption. So cinder cones are very common. But composite cone volcanoes are what get the attention of the public. These are also called stratovolcanoes. They exist within the well-known Ring of Fire on the Pacific Ocean, where nearly 80% of volcanism occurs. They're nearly symmetrical in their shape, with alternating layers of lava, which solidifies the rock, and ash, reflective of the eruptions. We have this concept of a nuée ardente. These are glowing avalanches. So in the pyroclastic flows after the eruption, they flow downhill, and they can reach these tremendous speeds of 125 miles per hour. And these are hot gases and fine ash. So they erupt up into the atmosphere, and then collapses on itself, and it rushes down as this pyroclastic flow. And these are tremendously deadly. So here I can look at the composite volcano and these stratovolcanoes, and these are some of the most beautiful mountains on Earth. But these are stratovolcanoes that are also composite volcanoes. They're synonymous. So these are interlayered, and let's just make sure we understand what takes place when we look within them. And they're located in and around the Pacific Ring of Fire. That these composite cones can be found all around here. Now, there's not a lot of them, but what ones do exist are really potentially deadly, and they could be planet changers. So here we have calderas. These are sunken volcanoes. So after an eruption, a magma chamber can empty and become void of materials. And if the overlying weight is greater than the support force of the volcanic base, it collapses unto itself. So these form semicircular calderas where the volcano collapsed upon itself. Mount Mazama collapsed to form Crater Lake. So beneath Yellowstone are a series of calderas, and I see it in this map right here, or this picture right here. And the overlying weight led to the internal collapse. These are erupting so much material that the land above it fell into it. And here's a caricature, kind of an explanation. We have these eruptions. The land cannot support it, so it falls on itself, and it creates a semicircular. And here's what I have for a picture there. So Crater Lake, this is the result of Mount Mazama, and here's what it would look like on a geologic map, and this is what it would look like for a bathymetric map. So it actually still has a little volcanic island within it. And Yellowstone, you gotta check this video out. This is a really cool video. And it's a little bit long, but it was aired nationally last year. It was really good, very well done. It's a little long, but I think you'll find it very entertaining. And then last but never least, we have basalt flows, flood basalts and fissures. And it's really just saying basalt kind of spills out through these fissures and pours out